Okay, good morning. We're getting started on the next unit today, which is the first of two trigonometry units. This is called Trigonometry A, and it deals with, I guess, what you would call trigonometric functions. Unit B in trigonometry is going to deal with trigonometric equations and also something called identities and trigonometric proofs. The first lesson it's a very important lesson to get off on the right foot. And it's a little bit longer than the second lesson of this unit, so I'm not going to hand back your exams today for you to look at. You're going to look at them tomorrow because we have a relatively short lesson tomorrow. So we're looking at trigonometry A, and the first lesson is on page 1 of your unit handout. We've got a lot of things on our plate this morning. We're going to review sketching angles in standard position, which is something that we spent a significant amount of time on or emphasis on in Math 20-1. And in Math 20-1, you were taught about positive rotation angles, and your teacher would have mentioned, but not made a big deal out of the fact that negative rotation angles have a particular direction to them. It's in this lesson that you finally understand the difference between radians and degrees. So when you were in junior high and you were bored in your math class and you kept hitting that button that said DRG on it, and on the screen it went from D to R to G to D to R to G, what you were doing was changing the unit that the angular measure was measured in. And you can use units of degrees, you can use units of radians, or you can use units of what are called gradians, which we never really use. I need to pause for a second and discuss something with you before I forget. All right. Sorry, Jonathan, I muted my mic and I didn't mean to. I was just explaining to everybody here that we're having a lockdown drill, and I was just explaining the procedure. So that's why there was dead space there for a minute or two. I wasn't thinking when I muted my mic. I apologize. So we're going to be sketching angles in standard position. We're finally going to learn what a radian is, and we're going to be talking about fractions of pi radians, which is a very important idea. Once you have identified what radians are, you should be able to convert between degrees and radians and degrees. So you need to be able to convert from one of those units to another. Think of it as like converting from miles to kilometers or kilometers to miles. It's just a different way to express the same thing. This is kind of a little piddly little thing that we need to know. You need to know about how big a radian is. And I can tell you one radian is about that big. It's about 60 degrees, approximately. It's not exactly 60 degrees, but it's pretty close. And then we're going to be talking about something which is called coterminality, which you did not study in Math 20. So there's a mixture here of things you studied in Math 20 trig combined with brand new ideas. So to begin with, we're going to define a radian. One radian is the angle created. The mathematical word is subtended. One radian is the angle created by an arc length. An arc length is a distance around the edge of a circle. It's along the curve of the circle. It's the angle created if the arc length is equal to the radius of the circle. So if you were to take a compass or something and draw a circle, and then you took a piece of string that was the length of the radius, and you carefully wrapped it around the edge of the circle, that would give you an angle of 1 radian. Just to take a look at this, there's the radius. If I peel off that radius and I wrap it around the edge of the circle, what I'm saying is this angle is 1 radian. And we abbreviate radian by just saying RAD. That would mean this is 2 radians and that is 3 radians. I just want to stop it there because I don't want to reveal something. I want you to notice that 3 radians came up almost to 180 degrees. Not quite. And that's why I've told you that 1 radian is approximately 60 degrees. It's kind of an important thing to note. Now it turns out that 180 degrees is not 3 radians. It's 3.1415926 to infinity, because pi is an irrational number. It's pi radians. And this statement right here is fundamental in this unit, that this is your starting point when you start talking about degrees and radians. 180 degrees is pi radians. By the way, I don't know if you recall, but in grade 10 and 11, your teachers should have been stressing to you or mentioned to you that whenever you write an angle in degrees, you have to put the degree symbol. If you don't put the degree symbol, it's radians. That's the rule. So we don't actually need to write pi rads. We could write 180 degrees equals pi. And it's understood that since pi doesn't have a symbol on it for a unit of degrees, that it's radians. So taking a look at this again, that's 3 radians, and then to there is just a little bit more. It turns out it gives you a total of pi. If you go all the way around, then that's 2 pi radians. So I mean, that to me that's kind of common sense. If pi rads or pi radians as an angle is 180 degrees, then 360 degrees would be twice as many radians. Now, I don't know if you recall, but in Math 20-1, there were these angles we called special angles. And special angles were angles like 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And the reason they're special, I don't know if your teacher taught you this or not, they didn't have to, but the reason they're special is they divide without remainder into 180. These special angles, 30 degrees, 45 degrees, 60 degrees, 90 degrees, they're considered special angles because they go into 180 degrees an integral number of times. Like there are, and you really need to understand these numbers, there are 6 30-degree chunks in 180. If you take a look at my arm, and I'm sorry, Jonathan, I'll put this on the board in a second, but if you take a look at my arm up here, not there, my arm is up here, 30 degrees, 60 degrees, 90 degrees, another 30, another 60, another 30, and another 30. It takes me all the way to 180. So when you're starting to talk about 30-degree chunks, yeah, it's not bad. 1, 2, 3, 4, 5, 6 30-degree chunks fit into 180 degrees. When you start to talk about 60-degree chunks, that's a little better. When you start to talk about 60-degree chunks, there's 60, there's another 60, there's another 60. So there are 3 60s in 180. 45, this is 0, there's 1, 2, 3, 4. 90, there's 1, 2. So these numbers all divide into 180 nicely. And that allows us to identify the exact values of some of these angles in radians, given the numbers in degrees. Obviously, 0 degrees is 0 radians. 30 degrees is pi over 6 rads, because 30 degrees fits into 180 degrees 6 times. You know, jumping ahead, we know that 180 degrees is pi radians. 360 degrees must be twice as many radians as pi. 90 has to be half of pi, because 90 fits into 180 twice. 60 fits into 180 3 times, and 45 fits into 180 4 times. I don't really believe it's to your advantage to set out to memorize this stuff. I think that's a mistake. I think it's better to understand the chunking of 180 degrees into little pieces, into segments. Okay? And that's going to be important for a little bit later. So, a review now of rotation angles in standard position. This has to do with what you were taught in Math 20-1. So as I go through this, I hope this is common sense, or maybe common sense is the wrong word. I hope you remember this. What a rotation angle is an angle formed by taking an initial arm and rotating it around what's called a vertex to a final arm, and the final arm is called the terminal arm. It's standard practice to put the initial arm on the positive x-axis and the vertex at the origin. And you need to know that a positive angle is in a counterclockwise rotation. So that rotation angle I have there is a positive rotation angle. And I want you to notice that there's an arrow on the end of this arc showing theta, which indicates a rotation angle has a direction. And if it's counterclockwise, which is that direction, it's positive. That's considered positive because then it sweeps through the 4 quadrants in numerical order. All right, as a warm-up here, you have another sheet. It's called Angles on the Unit Circle. Am I correct? Yes, it is. It's called Angles on the Unit Circle, and we want to write all of the positive rotation angles in both degrees and radians that are indicated on that diagram with dots. So I've got the top of the circle here. It's called the unit circle for a reason that we will get into on Tuesday? That we will get into on Thursday. So I think it's pretty obvious that when you go to the beginning, this is 0. And it's 0 degrees and it's 0 radians. So I guess I could put 0 and then 0 degrees. Let's go through quadrant 1 and 2 in degrees first. This would be 30 degrees. This is 60 degrees. And this is 90 degrees. And what I'm trying to highlight for you, and I will highlight it literally as well as figuratively, is the fact, this is 0, but the fact that all of these marks that I'm putting are multiples of 30. So if you take a look at the first mark, that's 0, the next one is 30, the next is 2 times 30, the next is 3 times 30, the next is 4 times 30. We're counting in chunks of 30. So this would be 4 times 30, which would be 120 degrees. Add another 30, we get 150 degrees. Add another 30, we get 180 degrees. Now what about the radians? Well, we know 180 degrees is pi rads. And we know that 90 degrees is pi over 2 rads. 30 degrees is pi over 6. Now watch what I'm going to do here. I'm going to count off, and I don't want you to necessarily mark up your diagram, but looking up here, if this is 1 pi over 6, then this is 2 pi over 6. I'm looking at those 30-degree wedges, but and everybody will get here sooner or later. You're going to realize very quickly, some of you, it's a lot easier to locate these angles by counting in radians than degrees. 2 pi over 6, well, this is just kind of my scrap work here. 2 pi over 6, the 2 over 6 reduces to pi over 3. So that's pi over 3, which makes sense. Because when you break up 180 into 3 sections, and again, don't mark up your unit circle, those are your 3 sections. Each of those 60-degree wedges is pi over 3. This one, I'm going to have to point with an arrow to help out anybody watching on video or watching at home right now. This is 3 pi over 6. 1, 2, 3 pi over 6. This is 4 pi over 6. Well, 4 over 6 reduces to 2 over 3. This one would be 5 pi over 6. So we're going 1, 2, 3, 4, 5, 6 pi over 6 all the way around. Now, I haven't forgotten about the 45-degree chunks. The blue highlights are multiples of the 30, and I want to be very clear here. the blue highlights, which are multiples of 30, happen to include the multiples of 60 and the multiples of 90. Because 30 goes into 60 and 30 goes into 90. But these green highlights are the multiples of 45. Starting at 0, this one would be 1 45 degree. This would be 2 45 degrees. This would be 3 45 degrees. And the 180, of course, is 4 45 degrees. But 45 degrees is pi over 4. I guess I should write 45 degrees here, and we can put pi over 4 as well. So this is 1 pi over 4, which means 90 is 2 pi over 4. Well, 2 over 4 reduces to 1 over 2. This would be 3 pi over 4. By the way, does everybody see, based on the counting of the chunks, that this right here is 3 pi over 4? You see it quite quickly, don't you? Can you figure out how many degrees that is? Requires a little more thought, doesn't it? It's more difficult or more thought involved in finding out an angular measure in degrees than it is in radians. It's 135 though, isn't it? So this is 135 degrees, but just looking at it and you know, looking at my arms, 1, 2, 3 pi over 4, it's really simple. 1, 2, 3 pi over 4. Okay, so now let's move on to the next quadrant. Quadrant 3 and then quadrant 4. Don't forget that we left off here at 180 degrees, which is also pi. This was 6 pi over 6 going all the way around. Which means this one, I'm going to do the radians first because it's just easier for me. This must be 7 pi over 6. Remember, the pi over 6's are these. Those are the 30-degree chunks. That's 7 pi over 6. This one, and again, I'm just putting marks here so that if you're watching this at home or on the video, you can see what I'm referring to. This one here would be 8 pi over 6, but 8 over 6 reduces to 4 over 3. And I don't want to drag this out too long, but I want to point out something important here. I've been counting in pi over 6's, and I ended up at 8 pi over 6 here, which reduces to 4 pi over 3. But I could have been counting in pi over 3's. Pi over 3 is 60 degrees. This is the one we're talking about being 4 pi over 3. There's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, which would make this next one 5 pi over 3 if we continued counting in pi over 3's. We don't have to, though. We could continue counting in pi over 6's. This was 8 pi over 6. This would be 9 pi over 6. Think about 9 over 6 as a fraction. It reduces to 3 over 2. So this is 3 pi over 2. And I didn't have to arrive at 3 pi over 2 by counting pi over 6's. I could have counted pi over 2's. Because this is 0, this is 1 pi over 2, this would be 2 pi over 2, this would be 3 pi over 2. There's lots of ways to arrive at these angular measures. So this one was 8 pi over 6. This was 9 pi over 6. This is 10 pi over 6, which reduces to 5 pi over 3. And this one here is 11 pi over 6. Let's put some degrees on this. This is 210 degrees. This would be 240 degrees. This would be 270 degrees. These are all going up by 30 each time. This would be 300, 330, and then I guess at the top here, I put 0 on the right-hand side, correct? But I could put 360 degrees or 2 pi. We still have the middle ones to go. These are 45-degree chunks. This is 5 45-degree chunks. It's 5 pi over 4. Because when I look at the 45-degree chunks, that's here, 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 and here. So there's 1, 2, 3, 4, 5 45-degree chunks. And 45 degrees is pi over 4. So that's why we have 5 pi over 4 there. This would be 6 pi over 4, but we already have it covered. This is 7 pi over 4. And we're done except for putting in some angles here. 180 plus 45 gives me 225 degrees here. And 270 plus another 45 gives me 315 degrees here. So pause there. Any questions with identifying those angles in either degrees or radians? All right. So let's do some examples. Convert the following degree measures to radian measures. Give your angles as exact values and as decimal values, and sketch the rotation angle. So let me ask you a question. Is 75 degrees a special angle? No. So you're not expected to just say, oh, I know how many radians it is. It's not that simple. What we're going to have to do is use a ratio. We know that pi radians is 180 degrees. And we want to convert 75 degrees to radians. So we can set up this ratio. Radians over degrees equals radians over degrees. When we cross multiply for x, you're going to end up with x equals 75 over 180. And it's going to be multiplied by pi. Now, pi is an irrational number. So if I say to you, and I asked my Math 20 students this question the other day, can you tell me what pi is equal to? And somebody said 3.14. And I said, well, no, it isn't. And they went, oh, okay. And they looked at their calculator and they said it's equal to 3.1415927, I think. And I said, no, because the decimals go on forever with no repetition. It's an irrational number. So the only way you can express pi as an exact value is exactly how it's written, pi. But the 75 over 180 we can reduce down. I think 15 goes into 75 5 times, and it goes into 180 12 times. So you can use the magic of your calculator here to confirm or let me know if 75 over 180 is 5/12. It is 5/12. So that means that this rotation angle is 5 pi over 12. And it's okay to think of it as 5 pi over 12s, or it's okay to think of it as 5 pi divided by 12. It doesn't matter. When we sketch it, and you have a ruler, if you want to use a ruler, you can. Although it's easier to locate radian measures for special angles, if I said to you, where is 5 pi over 12, that's a difficult thing to wrap your head around. Where is 75 degrees? Well, we know that. It's pretty close to 90. So this is theta equals 75 degrees, or 5 pi over 12. Does your printout say for the ration angle, or does it say for the rotation? Says this? Okay. Should say rotation. Negative 120 degrees. Hey, forget about the negative for a second. Is 120 degrees a special angle? It is. It's a multiple of 60. And you should know, I'm going to put the pressure on you here, you should know that 60 degrees is pi over 3 radians. And If this is two 60-degree chunks, then it's 2 pi over 3 rads. Now, could we have used a ratio to figure that out? Certainly. You could say pi rads over 180 degrees equals x rads over negative 120 degrees. When you cross multiply, you get negative 120 pi over 180, and 120 over 180 is 2/3. So how do we go about now sketching this? Well, in my mind, negative 2/3 pi, there's negative 1/3 pi, here's negative 2/3 pi. So we can put negative 120 here, or we can put negative 2 pi over 3. Okay with that one? All right, number 2, convert the following radian measure to degrees. We should not need a ratio to do this, because you should know 3 pi over 4 means 3 pi over 4s. So whether I say 3/4 pi or 3 pi over 4, it doesn't matter. You know that pi over 4 is 45 degrees. So that's 135 degrees, correct? Is my multiplication correct? Okay. By the way, you didn't need to recognize that pi over 4 is 45 degrees. You could have said this. How many degrees is pi? 180. Right? That's the starting point. That's what you need to know. So to convert this number of radians to degrees, we could have just taken 3/4 times 180, and you better get 135, right? Okay. So what does that look like? Here's the initial arm. The terminal arm is here, and this is theta, which is 3 pi over 4 or 135 degrees, whatever you would like to use. I'm realizing that we haven't done in decimal form yet, and we'll go back and do those right now. What is this angular measure in radians? Well, it's 5 pi over 12 radians. What is it? This is an exact value. What is the decimal approximation? Well, it's what we get when we calculate 5 times pi divided by 12 on our calculator. That's literally what it means. Pi here isn't an angle. Pi here isn't a variable. Pi in this context is a number. It's 3.14, on and on and on. So if we want the decimal approximation, then we just take 5 times pi divided by 4. So this angle is, sorry, not divided by 4, divided by 12. This angle is about 1.3 radians. And I hope you remember from the beginning that I told you 1 radian is about 60 degrees. So this kind of makes sense that 1.3 radians would be 75. So the decimal approximation is about 1.3 rads. If I were to take a look at what this is in radians, I would figure out what negative 2 times pi divided by 3 is, and I would get a decimal answer. Negative 2 pi divided by 3 gives me about negative 2.1 rads. So this is radians as an exact value. This one is radians as an approximate value. For the decimals in number 2, well, it's 135 degrees. It's exactly 135 degrees, so we don't need to play around with decimals. What about negative 11 pi over 6? Well, pi over 6 is 30 degrees. So this is negative 11 times 30 degrees. Or it's negative 11 over 6 times 180 degrees, because pi is 180. In either case, can you confirm you get negative 330? Okay, so negative 330 means we're going to start here and rotate negative 330, which is going to take us to this location 30 degrees shy of 360. So negative we rotate clockwise, right? By the way, I would say to you that negative 11 pi over 6, if you look up here, this is 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10, negative 11 pi over 6. You can count off those chunks. And lastly, 6.5. 6.5 what? Is that degrees or radians? Reagan, do you know? Why do we know it's radians? Don't know? It's a lucky guess. Why do we know it's not degrees? Pardon? There's no degree symbol. So I'm giving you this example because some people tend to come out of this lesson and think, oh, well, it's only radians if I see the letter pi. But I can have a decimal radians. This is 6.5 rads. And the only way that we're going to figure out what this is equal to is to use a ratio. Now, normally I would use pi rads over 180 degrees, but I'm going to use 180 degrees over pi rads because the thing I'm trying to find is degrees, and I would prefer that my unknown is on the top of an equation that has fractions in it. And this is over 6.5. If you cross multiply, you get x equals 6.5 times 180 degrees over pi. So we need to figure out what 6.5 over 180 is. I want to say 630. And I would be wrong. 810. I'll just shout out random angles, see if I get it eventually. So you want 6.5 times 180. I'm going to give you my third answer in just a second. 1170. Thank you. 3 times lucky. I get 1170 over pi, and these are degrees. So here's a little tip for you. It doesn't have to be this way, but anytime you have an angular measure as an exact value in degrees, you can express it with pi in the denominator. But if you see pi in the numerator, it's probably an angle in radians. So this is degrees. This is the exact value. Now, if you want to figure out what that is as a decimal approximation, then we can take 1170 divided by pi. And by the way, it's probably important to calculate it in degrees to draw it. I don't know what we're going to draw unless I see it in degrees. Well, I kind of do, but we'll get to that in a second. So what we get is 372 degrees. Now, by the way, I knew that this angle was a little bit more than 360. We'll draw it in a second. I knew it was a little bit more than 360 because 6.5 is a little bit more than double pi. When we say that this is 2 pi all the way around to this point, 2 pi is about 6.28. If you take 2 times pi, you get about 6.28. So anyway, 6.5 rads is, did we had 372? Was that what it was? So it will be, here's your initial arm, here's 372. And you do need an arrow on the end of your arc. So that's theta. And you can write theta equals 6.5 rads. You can write theta equals 1170 over pi degrees. It's entirely up to you. Any questions with that last example in this section? Go ahead, Ian.
What were you saying about having pi on the bottom and pi on the top?
I'm just saying that if you have an exact, if you do a conversion to degrees, and it's an exact value when you went from decimal radians to an exact value in degrees, you're going to end up with pi on the bottom. So when you see it on the bottom, the units are most likely degrees. Whereas when you looked at converting degrees to radians, so this was decimal radians into exact degrees, and there's a pi on the bottom. When you look at decimal degrees, when you take a look at decimal degrees to an exact value of radians, the pi is on the top. It's just a visual reminder. All right, let's take a look at now pretty much the final thing here, and it has to do with a property of angles called coterminal. If you look at the word coterminal, same terminal. So it is possible to arrive at a destination. Let's say that this is the destination we're talking about, and this is your starting point. It is possible to go from the starting point to your destination in a lot of ways. One of the ways I can do it in this diagram is I can rotate 50 degrees in a counterclockwise direction. But if I rotate 420 degrees, I'll end up there as well. Can I get you to wrap your head around why 420 gives you the same location as 50? I want you to sort that out in your head right now before I explain it. What is it about those numbers, 50 and 420, that make them have the same terminal arm, which makes them coterminal? So hand up and down if you know. What is it, Marcel? Right. If you're anywhere on the grid, what Marcel just said is you have to add 360 to 50 to get 420. If you're 410, I've been saying 420, but it's 410. If you're anywhere on the coordinate grid, to get to the same location, you can go another 360 degrees in either direction. So I could take 50 and add 720, couldn't I? That would give me another coterminal angle. So let's take a look at a few quick examples here. Sketch a rotation angle of 60 degrees. That's pretty straightforward. Here's the initial arm. Here's the terminal arm. We can label it as theta equals 60 degrees. What are some examples of coterminal angles? Well, again, we don't want to have to draw all of these. We want to get a little bit more conceptual in our thinking. To go from one location to the same location, you just have to travel 360 degrees more or 360 degrees less. So if I take 60 and add 360, this is a coterminal angle. If I add 360 again, this is another coterminal angle. If I take 60 and subtract 360, this is another coterminal angle. There's an infinite number of coterminal angles. I could keep adding and subtracting 360 all day long. And we'll come back to that idea in a bit. So what I have on the board here, these three are three coterminal angles. Any questions with 3? A or B? All right, what about negative 275? Well, I know negative 270 if you look at the board. This is 0, so this is negative 90, negative 180. This is negative 270. So negative 275 is just a sliver past negative 270. And I would say to you, you know, that's even too big. I don't want to get the protractor out, but 5 degrees past 270 is going to be just a little bit past 270. It's going to be like that maybe. Maybe that's even too big. But, you know, we don't have to break out the drafting tools here. I can label this as theta equals negative 275. And if I want some coterminal angles, I go to the calculator and I take negative 275. Let's add 360. 85 is 1. Let's add another 360. 445. I'm going to subtract from 445. I'm going to subtract 17 times 360. I hope you understand this is going to give me a coterminal angle because I'm subtracting 360 again and again and again, 17 times. And again, I'm leading up to something that concludes this lesson. So there's another coterminal angle. And I might as well reveal this little idea to you right now, that the coterminal angle in this particular question could be any angle that's negative 275 degrees plus a multiple of 360 degrees, as long as that multiple, well, I'll go plus or minus, as long as that multiple is a natural number, 1, 2, 3, 4, etc. You can add 1 360 or 2 or 3. I can take away 1 or 2 or 3 360s. So you could just use this formula, put in any natural number you want, and decide on positive or negative. This gets a little bit trickier with 5 pi over 6. 5 pi over 6, by the way, is right here. The reason being, pi over 6 is 30, so if you take a look up here, this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. 5 pi over 6 is 30 degrees shy of being 180. So we're going to have to take 5 pi over 6, and if we want to add a full revolution is 2 pi, right? We want exact values. We don't want to go 5 pi over 6 on our calculator plus 2 pi. We'll get these weird, wacky decimals. So what I'm going to do is think of 5 pi over 6 as 5 pi over 6. It's 5 pi over 6s. And I'm going to think of 2 pi as 12 pi over 6s. I mean, look at the diagram up here for a second. This is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. 12 pi over 6 is a full revolution. I mean, you could also just convert this to a common denominator of 2. So I am going to take 5 pi over 6 and I'm going to add 12 pi over 6. Well, you know, $5 plus $12 is $17. So 17 pi over 6. I can't really do this with my calculator. Could I take 5 pi over 6 and subtract 12 pi over 6? Yeah. Well, if I have $5,000 in my bank and I spend $12,000, then my bank balance will be negative 7. 5 minus 12 is negative 7. Could I take the 17 pi over 6, which we arrived at by adding 12 pi over 6, and add another 12 pi over 6? Sure. And if I add another 12 pi over 6, 17 plus 12 is 29. You know, we could go on and on all day. As long as you keep adding 12 pi over 6 or taking away 12 pi over 6. In other words, as long as you're doing this, where n is a natural number, you will get coterminal angles. By the way, when you write this that I've just written, you don't need to write 12 pi over 6. You could just put 2 pi. But to find the angles requires that you probably think of it as 12 pi over 6. So that one was a little bit different. Does anybody have any questions with number 5? Did we go from 3 to 5? Was there a 4? And we did it? Okay. Negative 3 pi over 4. Well, looking up here, pi over 4 is 45. This is 0, negative 1, negative 2, negative 3 pi over 4 is here. So what are some coterminal angles? Well, we're going to have to add a full revolution or take away a full revolution. So we can take negative 3 pi over 4 plus a full revolution, which is 8 pi over 4. This is 2 pi, which is a full rev. Why am I going in quarters? If you think about what I did in the previous question, I made a big deal out of doing this. That is one of the most lopsided circles I've ever seen. I made a big deal of saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pi over 6. I did that because we were adding multiples of a full revolution to, I believe it was 5 pi over 6. It was pi over 6s. In this question, we are adding a full revolution to 3 pi over 4s. So when you take a look at a circle, 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7, 8 pi over 4. Which, I mean, you can easily see that the number 2 is 8 over 4. You could find a common denominator. Anyway, what do we get? 5 pi over 4. I could add another 8 pi over 4, 13 pi over 4. I could add another pi over 4, but I'd like to get at least one more negative coterminal angle. So I'm going to take the negative 3 pi over 4 and subtract 8 pi over 4, which gives me negative 11 pi over 4. Any questions with 6? So we have one last question here, and it has to do with something called a general expression. Express the angles coterminal with 130 degrees in general form. If you look at the top of the screen, general form means list all of the angles. Now there's an infinite number of coterminal angles to 130 degrees, so I can't write them all out, but I can write that all of the coterminal angles to 130 degrees would be expressed as 130 degrees plus or minus n times 360. Where n is a natural number. Good? What about coterminal angles to 7 pi over 3? Well, it would be 7 pi over 3 plus or minus n times 2 pi, where n is an element of the natural number sets. There's no need to write n times 6 pi over 3 there. Now I have one final thing I need to address with you. Overall, though, lesson went good. You kind of get the gist of everything we've talked about. All right. I have one more thing I need to show you because your textbook makes this mistake in places and it's not forgivable on an exam. Okay? What your textbook will say in places is that the answer to this is 130 degrees plus n times 360, where n is an integer. And the reasoning is, this is very tricky, because what I've written in green will become an acceptable answer for something else later, but it's not an acceptable answer for coterminal angles. Their reasoning is that since an integer can be positive or negative, that takes care of the plus or minus. Does anybody see the problem with saying that, though? It's so subtle, but it's a problem. It's wrong. other than positive and negative whole numbers, what else do integers contain? They don't actually contain decimals. They are either positive or negative natural numbers, but they contain one other thing. Shazmaida? They include 0. And I know this may seem very, very picky, but if you put 0 into that green equation, you're going to get a coterminal angle of 130 degrees, right? It's wrong to say that an angle coterminal with 130 degrees is 130 degrees. A coterminal angle is a different angle that has the same terminal arm. So you don't want to do this. This is not correct for coterminal angles. It will be correct later when we're solving equations where we want to include that first angle, but it's not correct right now. You must say for coterminality plus or minus n times 360. Could you do this? I mean, I'm not saying you can't do what I've written in green. You would just need to also say that. That's okay. The integer element part of the notation tells you it could be plus or minus. And then you go, oh, but I can't use 0, so I'm going to say n cannot be 0. So there are other ways to communicate your answer. Anyway, the goals today were for you to become familiar with common rotation angles in radians, multiples of pi over 6, multiples of pi over 4, multiples of pi over 3, multiples of pi over 2, to be able to convert degrees to radians and vice versa. We'll talk more about that tomorrow. And also the concept of a coterminal angle and how to find coterminal angles was also covered.